Hello, and thank you for tuning in. My name is Emmanuel Costantino, and I am the Program Manager for the SWARM-EX team. This video serves as an introduction to the SWARM-EX mission. The Space Weather Atmospheric Reconfigurable Multiscale Experiment, or SWARM-EX for short, is an NSF-sponsored mission to develop and launch 3 3U CubeSats to advance formation flying and swarm technology while addressing outstanding questions in aeronomy. The string of pearls formation, illustrated here, will eventually scale up to dozens of large swarms operating at various altitudes and in different orbital planes to solve other open questions in aeronomy. The SWARM-EX team spans 6 institutions across the country. The mission is student-led and supervised by faculty at each institution to allow students to flourish in their respective subsystems. The SWARM-EX mission has 3 overarching objectives: a science objective to take measurements of the upper atmosphere, and an engineering objective to demonstrate novel technologies. In addition to its technical goals, SWARM-EX seeks to use CubeSat development as a vehicle for education and public outreach. We will give a brief overview of all 3 of the objectives in the following slides, starting with science. SWARM-EX's 2 primary science questions focus on understanding the coupling between the equatorial ionization anomaly, EIA for short, and the equatorial thermospheric anomaly, ETA for short, in low Earth orbit. The EIA graph on the top right shows the electron density, while the ETA graph on the bottom right shows the mass density of atomic oxygen. The interaction between the Earth's magnetic field and eastward dynamoelectric field creates an E cross B force that lifts the ionospheric plasma in the vertical direction. The plasma rises to the top side ionosphere, but then gravity and a pressure gradient force the plasma back downward to an altitude of about 400 kilometers. The diffusion along magnetic field lines yields 2 crests with maximum ionization density around plus or minus 15 degrees magnetic latitude, with a local minimum at the magnetic equator. The plasma flow, which mimics the curve of a fountain, is known as the fountain effect and leads to the dual band of enhanced plasma density on either side of the magnetic equator, that is referred to as the EIA. The ETA has been observed as a concentration of neutral particles in the thermosphere. These particles are concentrated around plus or minus 25 degrees magnetic latitude, with a significant reduction in particles at the magnetic equator, very similar to the EIA. The ETA is described as being caused by ion drag and charge exchange released chemical heating, and is predicted to be caused by the interaction between the neutral molecules and plasma ions. This would explain why the ETA features look magnetically aligned despite being neutral. In contrast with the EIA, the ETA is much more of a mystery to the scientific community because measurements of the neutral density would need to be taken in orbit, whereas the electron density can be easily measured from the ground. SWARM-EX, however, will have no problem taking critical in situ measurements of both the electron and neutral density to observe the EIA and ETA features for timescales of less than a single orbit. Here, we can see what atomic oxygen and oxygen ions look like at an atomic level. Atomic oxygen is orders of magnitude more reactive because it is a diradical neutral. That is, it has 2 valence electrons. This makes it detrimental to materials commonly flown on spacecrafts. Additionally, it is the main contributor of orbital drag in low Earth orbit. Even at these high altitudes, oxygen particles, which are the most dominant particle in low Earth orbit up to 500 kilometers, slow spacecraft down and cause them to gradually deorbit. The production of atomic oxygen ions leads to the production of free electrons. These electrons contribute to unwanted spacecraft charging and cause GPS scintillation, an undesirable phenomena which causes errors in GPS estimates by disrupting the power and phase of GPS signals. Similar to atomic oxygen ions are the dominant charged ions in this region of the atmosphere. The first primary science question seeks to understand how persistent and correlated are the plasma density and neutral density features in the EIA and ETA. The second question addresses the timescales at which we observe changes in the EIA and ETA properties. Here, we are looking to explore what happens when the features are not persistent. The animation on the right shows us the string of pearls formation of the spacecraft for a single orbit, as well as the predicted oxygen ion density that each spacecraft would measure. Notice that the three density curves on the far right are shifted in time, due to the fact that they measure the EIA properties at different times in the orbit. The science questions cannot be answered with a single orbiting spacecraft and require the full constellation of spacecraft to be completed. Next, we will introduce the engineering objectives of SWARM-X. Using cutting-edge orbital guidance, navigation, and control algorithms, SWARM-X will demonstrate formation flying capabilities, collision avoidance, and reconfiguration of the swarm. This will be done using a mix of differential drag and onboard propulsion. Propulsion is not often used on CubeSats and poses an exciting challenge to the SWARM-X mission. The use of differential drag and onboard propulsion allow the swarm to take science data across large swaths of the atmosphere, but also demonstrate reconfiguration capabilities. Finally, SWARM-X will demonstrate an ultra-high frequency crosslink between each of the satellites in conjunction with a code division multiple access downlink to send science and health data back to Earth. Code division multiple access, or CDMA for short, is not limited by a single frequency band or time interval for a given channel. Rather, each channel is assigned a unique code, known as a spreading signal, that allows multiple users to use any frequency at any time. Suppose you have some data signal you would like to send, represented here by 1 and -1. The data is multiplied by a higher frequency spreading signal to produce the signal to be transmitted. The signal is now unrecognizable from the original data. Back on Earth, the signal is then decoded by the receiver to access the original message. The third and final objective of the SWARM-X mission is the education and public outreach effort. SWARM-X spans 6 institutions across the nation, each with differing levels of CubeSat experience. The students participating in this project range from first-year undergraduates to PhD candidates. Their progress and engagement are tracked throughout their time in SWARM-X. There are 11 subsystems working together to ensure the success of the SWARM-X mission. These subsystems can be seen below. The science and instrument subsystems assure that the primary science questions can be addressed and that the instruments chosen for the mission are sensitive enough to capture the appropriate science data. The electrical power system distributes the electrical energy from the solar panels across all electrical components on the spacecraft. EPS also measures the state of charge of the batteries and powers components on and off based on the commands sent by the Command and Data Handling subsystem. The Command and Data Handling subsystem runs the flight software for the mission. CNDH routes information to and from all of the subsystems and sends commands that control the spacecraft. The flight software allows for the spacecrafts to fly autonomously, but commands can also be sent from the ground to operate the spacecrafts. CNDH can be thought of as the brain of the satellite. Using sun sensors and a star tracker, the attitude determination and control system is able to estimate how the spacecraft is oriented with respect to the Earth. Additionally, ADCS is capable of changing the spacecraft's orientation depending on the mission's needs with the use of reaction wheels. The ADCS tells us how the spacecraft is oriented, and the Orbital Guidance Navigation and Control subsystem tells us the position and velocity of the spacecraft at a given time. The position, velocity, and time data is used to achieve formation flying, avoid collisions ahead of time, and to reconfigure the swarm. The propulsion units used for the SWARM-EX mission are made by the SWARM-EX team. Along with the use of differential drag, the cold gas propulsion units serve as the primary way to move the spacecrafts to avoid collisions and reconfigure the swarm. In order to send the science data and the health and status of the spacecrafts down to Earth, the communication subsystem uses a mixture of a novel X-band link and a UHF link to downlink data. For intra-satellite communication, a UHF crosslink is used, which is critical for reconfiguration, collision avoidance, and formation flying. Satellites often experience extreme temperature variations throughout their lifetimes. To ensure that the onboard components do not become too hot or too cold, the thermal control system uses a mixture of passive cooling and active heating to regulate the spacecraft temperature. The structures team is tasked with designing the satellite bus and integrating all the flight hardware into and onto the satellite as a single unit. The satellite is designed by the team such that it can fit into a CubeSat deployer and meet the mass requirements for launch. The systems engineers are concerned with the cohesion and integration of the subsystems. By working individually with each subsystem and understanding the overlap between them, the systems engineers ensure that all the subsystems can work together to achieve the mission's goals. CubeSat development is broken up between the 6 institutions at the subsystem level. This allows students to reinforce their current knowledge of spacecraft design and the opportunity to branch out into new fields. In summary, the SWARM-EX mission is an exciting endeavor to learn about the Earth's atmosphere using novel technologies while allowing for collaboration and academic growth across various institutions. Thank you for tuning in, and we'll catch you next time.